Okay, welcome everybody. Today we have Cosma Fulga from Dresden, and he will talk about non-Hermitian physics without gain or loss, special title, The Skin Effect of Reflected Waves. So when you're ready, Cosma, just go ahead.
Thank you, and thank you very much for inviting me to give this talk. So this is recent work done in collaboration between IFW Dresden and Aachen University. This was done together with Jeroen van den Brink, Fabian Hassler, who's from Aachen University, Victor Koenier, who is a postdoc in my group, and Selma Franca, who was a PhD student and now she's a postdoc in Grenoble. So this is a talk about non-Hermitian topological phases. And I think a good starting point would be to talk about conventional topological phases as a starting point. So one of the best known topological phases is the Chern insulator. This is a two-dimensional system which has a gapped bulk. So there's a gap separating a valence band and a conduction band. And if you have a boundary to another system like the vacuum, then the Chern insulator will have a chiral edge mode or a number of chiral edge modes on its boundary. So I'm showing these in blue. So these are unidirectional. They move in one direction. You can see they have here only one sign of their velocity. Now, if this Chern insulator is semi-infinite, if this boundary to the vacuum is infinitely long, then one property you will have is that you will have boundary states at all energies inside of the gap. So the boundary states will completely fill the energy range of this bulk gap densely. If you have a finite size system, then you're going to get finite size effects, like in the simulation where you can see there's a discrete number of these boundary states throughout the gap. And this was the first observed topological phase in the 80s and the quantum Hall effect. And since then, many more kinds of topological phases have been developed and they are now better understood. And more recently, some of the new types of topological phases that people have started looking into are so-called non-Hermitian topological phases. So in a non-Hermitian topological phase, I have a system which is described by a non-Hermitian Hamiltonian. So it's a bit harder for me to plot band structures like I showed you on the last slide. So instead, something that's common is to plot the spectrum in the complex plane. If the Hamiltonian is not Hermitian, then its eigenvalues can be complex. And if they are complex, I plot them on this real axis, imaginary axis. Now, I can do this also for the Chern insulator I showed you before, and the spectrum of the Hermitian Hamiltonian would look something like this. You can see there's a valence band here at negative real energy, and there's a conduction band at positive energies. This is inside the bulk of the system. And on the boundary, I have these blue edge modes, which completely fill the space between the two bands. In a non-Hermitian system, I can, of course, have other kinds of spectra. They're not forced to lie on the real axis of this plot. So in particular, I could have a spectrum that looks like this. This is the spectrum of some Hamiltonian, which is not Hermitian. And you can see it forms a closed loop in the complex plane. Now, here I can also talk about notions such as a gap. There's a region in the complex plane here close to the origin, and there's no spectrum here. This is like a gap. And if I want to move from this region to somewhere at some large value of outside of the circle, I can only do this by crossing the spectrum. So just like here, I could only go on the real axis through a gap if I wanted, through a band, if I wanted to move like from below this valence band to above it. Here, the only way to cross from, let's say, a point over here to a point over here is to intersect the spectrum of the Hamiltonian. So in this sense, there are two gaps in this system. There's one gap which contains the origin of the complex plane, and there's a second gap which is distinct, and it contains the infinity, the complex infinity. So these are two distinct gaps, and they're called point gaps.
There's a question from Philip. Philip?
A very quick one. The picture you've drawn of ME and real E, assume it requires the Hamiltonian to not just be Hermitian, and to not just be not Hermitian, but to also be PT symmetric. Are you going to just look at PT symmetric systems?
No, I'm not. I'm not going to look just at PT symmetric systems. So the picture I drew here is just an example, but you could imagine a sum operator which has a spectrum which is like over here, for instance. Okay. You can have a closed loop anywhere you like in the complex plane, in principle. And if you have a closed loop in this spectrum, then you have two well-defined point gaps. Here, for simplicity, I'm drawing one which surrounds the origin of the complex plane, but it's in general, it could in principle be anywhere.
Okay, and if you relax the PT symmetry, when you do so, will you comment on what happens to unitarity?
Yes, so here, if this circle is, if you think of it as being the unit circle in the complex plane, then this operator is unitary because all of its eigenvalues lie on the unit circle. But in principle, you could break this unitarity. So for instance, you could have an ellipse instead of a circle. Yeah. So so far on this level, I'm only talking about possible spectra of non-Hermitian Hamiltonians without restricting them to particular kinds of Hamiltonians which have symmetries. But throughout this talk, you'll see later on that I'm going to focus on specific kinds of operators, and these are unitary under some conditions.
Okay.
Now, this point gap can also be topological. Just like in the Chern insulator, there was a gap in the bulk, and this was a topological gap. This produced boundary states throughout the gap. Here, this is a two-dimensional region of the complex plane, which is a point gap, and this can be topological as well. In which case, introducing a boundary and having a semi-infinite system would lead to a spectrum that looks like this. Similar to conventional topological phases, everywhere inside of this gap, you will have boundary states present in the system. Now, of course, this is for a semi-infinite system, whereas for a finite system, you're going to get finite size effects. So you're just going to get a discrete number of points, which depends on how large your system is, but these will be inside of the gap of the bulk of the system. So this is a way you can generalize the idea of having edge states in a gap, boundary states in a gap, but now the gap is a two-dimensional region of the complex plane instead of a one-dimensional interval on the real axis. So one of the simplest models.
Just very quickly ask a second question. In that blue region, is the density on circles the same?
Yes. So yes. So you can one way to think about it is there is a semi-infinite system. So there are infinitely many eigenvalues of this semi-infinite system, and for any single point inside of the unit circle, there is one mode localized on the boundary of the system. It's just like here, for any single point in this real axis interval, you will find one mode localized on the boundary of the system if the Chern number is 1. So here's how it works in a Hamiltonian. This is called the Hatano-Nelson model. It was introduced by Hatano and Nelson in this 96 paper, and it's one of the simplest examples of a Hamiltonian showing non-Hermitian topology. So this is a chain of single orbital sites. It has nearest neighbor hoppings, J left and J right. I take them to be real numbers, these hoppings. And the hopping to the left here is larger than the hopping to the right. So I'm showing this with arrows here. The thick arrow means the hopping to the left is larger than the hopping to the right. This makes the Hamiltonian to be non-Hermitian, because normally you would need to have equal magnitude hoppings if you want to have in the opposite directions, if you want to have a Hermitian Hamiltonian. So now this Hamiltonian is not Hermitian anymore because of the different strength of the hopping. And it also becomes a topological Hamiltonian. So there's a topological invariant describing the fact that this Hamiltonian is topologically non-trivial, and this is the winding number of its bulk spectrum. So if I Fourier transform this and I go to momentum space, I will find that the spectrum forms a closed loop around the origin of the complex plane. Here I'm drawing a circle for simplicity, but in general, the spectrum will be an ellipse where the semi-axes of the ellipse are the sum and the difference of these two unequal hoppings. And this closed loop has a winding number associated to it. So this Hamiltonian has only one band. So if I start to plot the spectrum of the Hamiltonian and gradually change momentum to go across the full one-dimensional Brillouin zone, I will see that this eigenvalue goes around and the band winds in the complex plane. So this is this spectrum has a winding number W, and this is the general formula for the winding number. And here it's +1 if the spectrum winds in this direction as shown here. And this is a topological invariant, which tells me this one-dimensional system is topologically non-trivial. Here I'm writing the general formula, which involves the determinant of the Hamiltonian. For a simple one-band system like the Hartano-Nelson model, you don't need the determinant because h of k is a scalar. But in general, if you had a multi-band system, you would have to take the determinant, and then the collection of all the bands would collectively form a non-zero winding in the complex plane. So this topological invariant of the Hartano-Nelson model, it produces some physical consequences on the Hartano-Nelson model. And these are two of them. First of all, because of the non-zero winding number, you will find boundary states in the system. So if you take a semi-infinite system or a finite size system for that matter, you will see that all of the eigenstates of this system, they are localized at one end of the chain. So the left eigenstates are localized on one end of the chain, and the right eigenstates, since it's a non-Hermitian Hamiltonian, are localized on the other side of the chain. But this winding number predicts the appearance of localized boundary states. So this is very similar to conventional topological insulators. They also have boundary states which are predicted by non-zero topological invariants. Here, this non-zero topological invariant predicts the formation of boundary states. But the only difference is now every single state in the system is a boundary state. So if I take this finite size system with however many sites I drew here, I will see that absolutely every state is exponentially localized to the boundary. This is called the non-Hermitian skin effect. It's a way of saying, it's a name people have found to express the fact that all of the states are boundary states if you add a boundary to the Hartano-Nelson model. There's a second signature of non-trivial topology in the system, and this is a bulk signature. It turns out the non-zero winding number has been related, in this paper, has been related to a non-zero net bulk current. So if I start with some wave packet localized in the bulk of the system, this is not an eigenstate, so it will evolve in time. And when I apply the time evolution operator to this initially localized wave packet, I will see that the wave packet will move in one direction. So intuitively speaking, the wave packet will move in the direction of the larger hopping. Larger hopping means more current. So there's a net current. All wave packets will move in this direction, and eventually they will hit the boundary of the system, and they'll stay there at the boundary of the system, forming the non-Hermitian skin effect. Now, these are the two signatures of non-trivial topology in this simple model. One of them is a bulk signature, a net non-zero current in the bulk, and the other one is a boundary signature, the non-Hermitian skin effect, which are both predicted by this non-zero winding number, this topological invariant. Now, just as a thing which I will use later on, here this arrow denotes time evolution. So time evolution means I am applying the exponential of the Hamiltonian. But in practice, if I have a state here and I apply just the Hamiltonian itself, the Hamiltonian itself is the generator of time evolutions. So then if I apply the Hamiltonian to this particular wave packet, I'm still going to get a wave packet which is slightly shifted in the direction of the non-zero current. Okay, so when Hartano and Nelson wrote this model, they were thinking about a system which exists in real life. And the system they were thinking about is looks like this. So this is how the Hatano-Nelson model might look like in a real life system. This is a figure from their paper. So what you see here is a cylinder. It's a hollow cylinder, which is made from a superconducting material, and it has these defects in it. They call them columnar pins. So this is inside this cylindrical shell, there are all of these line defects, which are columnar pins. And what they did was they considered applying a magnetic field along the axis of the cylinder. For a strong enough magnetic field, this will produce flux lines. So these wavy things here are the flux lines produced by the magnetic field. And these will like to stick to these defects. They preferentially exist at the place where you have these columnar pins. These pins pin the flux lines to various places of the cylinder. And then they considered applying a current through the center of the cylinder, which will produce a magnetic field in the angular direction. And this will twist all of the flux lines. So you see here an example of a flux line, which goes from the bottom to the top because of Hz, but is being twisted in a particular direction here, counterclockwise, because of this H perpendicular. Now, this is a fully Hermitian system. This is a two-dimensional cylindrical superconducting shell, which is placed in a magnetic and an electric field. However, if you think about the direction along the cylinder as being a kind of time, then you can reduce the problem to a one-dimensional problem on a ring. So then effectively all of these flux lines, they describe the evolution of some kind of particles as a function of tau, which is time effectively, a direction along the cylinder. And then you will see that these particles, they hop from one side to the other, from one columnar pin to the other, but they hop preferentially in one direction. That's how you get a non-reciprocal hopping in this model. The magnetic field twists the flux lines, and this maps to a model, an effective one-dimensional model, where the hopping in one direction is larger than the hopping in the other direction. That's one way to get non-Hermitian Hamiltonians. If you want time to be time, however, if you generally do non-Hermitian systems by thinking about gain and loss. So physically, a non-Hermitian Hamiltonian is usually understood as saying that the complex eigenvalues, the energies, are formed of a real part and an imaginary part. And the real part encodes the excitation energy of a particular mode, whereas the imaginary part encodes the decay or amplification rate of this mode. So from a physics perspective, you usually think of non-Hermitian Hamiltonians as systems which have some kind of coupling to external degrees of freedom, such that their modes can have decay and amplifications. And there are many ways to do this. This is a table I have copy-pasted from this review paper on non-Hermitian physics, which is very nice. I recommend it. And you can see there are many different ways to obtain physically non-hermiticity. And they all involve some kind of gain and loss. You can have gain and loss of photons. You can have friction and heating, which dissipate energy, radiative decays, dissipation, or finite lifetime quasi-particles in a many-body system. So all of these are coupling the system to external degrees of freedom. And many of these systems, many of these physical mechanisms have already been used to realize topological non-Hermitian systems. So this is a slide which collects only a few of them. There are many more such kinds of systems which show non-Hermitian topology, and I have collected them here because they all show a different kind of platform in which to obtain non-Hermitian physics and non-Hermitian topology. So here on the top, you have a optical setup. These are some fiber optics cables, and the light goes around and around in these fiber optics cables, and this mimics the evolution of quantum particles through a chain. And here the non-hermiticity is done by these acousto-optic modulators. These are devices that pump energy in and out of your fiber optics cable, so they can change the amplitude of the light going around in these cables. Here on the right side, you have a chain of boxes. These boxes are hollow, and they act as sound resonators. So this is an acoustic system, which is a chain of resonators for sound. And so the sound resonance can hop left and right in this chain. And the way they make this system non-Hermitian is by using these little black boxes, which are sound amplifiers. So these little black boxes, they're connected to the inside of these hollow chambers, and they produce gain and loss into these resonating sound chambers. And this costs energy. These little black boxes, you have to plug them in because otherwise they don't function. In the middle here, you have a chain of coupled pendulums. These little red things, they can spin. So these are like pendulums, and they're connected to each other by springs, which are shown in blue. So this is an array of pendulums connected by springs. And the way they make this system to be non-Hermitian is by adding motors. So there are electrical motors at the back, and these motors put a force on these. They pump energy into this chain of coupled pendulums. Here on the bottom, you have an electric circuit made of resistors and capacitors, and the resistors, they dissipate energy. So this produces non-hermiticity. And here on the right, you have a recent work on a optical lattice, so an ultra-cold atom system, where they have a chain, effective chain of atoms. And here the non-hermiticity is more familiar in terms of quantum physics. They actually have a reservoir, and atoms can hop in and out of the chain into the reservoir and form the reservoir. So this produces an effectively non-Hermitian description. You can describe these systems using non-Hermitian Hamiltonians. Okay, so I'm going to show you how to get non-Hermitian physics without gain and loss. And to do that, I'm going to look at the following problem. So this in the middle, this blue thing is a Chern insulator. It's actually the toy model I showed you from before is this system which has a gap in the bulk, and this is the chiral edge state, which moves all around the boundary of the system. Now, I'm taking this Chern insulator and I'm placing it in a two-terminal transport geometry. So there's a lead here. You can think of it as being a metallic lead if you're doing electrical transport, or you can think of it as being some kind of waveguide if you're thinking more along the lines of optics. But okay, this is a waveguide and it supports propagating waves. This is the second one. So you can study how these waves are scattered by the presence of the Chern insulator. So the modes inside the lead, these are the modes inside the lead. They have a plane wave form. So they can write them like this. This is the plane wave part of the waves. This tells you if the wave is moving to the left or to the right. And this is the second part, which is the transversal component of their wave function. So this can tell you, for instance, if the incoming wave is spin up or spin down. But it can also tell you whether the incoming wave is positioned in different parts of the waveguide. So I could imagine somebody is requesting remote control of my screen. Do I approve?
No.
I decline.
Yes,
okay.
You decline.
Okay, I declined.
That's weird. Keep going.
Okay, so basically the transversal part of this wave function tells me the properties of these states in the direction perpendicular to the waveguide direction. They can tell me if I have a wave in this place or in this place, but they can also tell me about their internal degrees of freedom, such as spin. Okay, now these incoming and outgoing waves, these waves propagating in opposite directions, they're related to each other because they get scattered by this Chern insulator. And this is described by a scattering matrix. Scattering matrix is unitary and relates incoming states to outgoing states. In a two-terminal geometry, it has this form. It's composed of reflection blocks. These tell you how the waves get backscattered into the same waveguide. And the off-diagonal blocks, they are transmission blocks. They tell you how waves that, let's say, come in from this waveguide get transmitted to the opposite waveguide. Now, there is one mode which connects the left and the right waveguide. This is the chiral mode. So a wave that comes from here, it can propagate, let's say, through this chiral mode and then end up on the other side. But this is one mode, and the density of states of this lead, let's say, is very high, which turns out to mean that most of the waves here are reflected. Most of the waves coming from this high density of states waveguide, they get back reflected. And this is described by a reflection matrix, which maps incoming to outgoing modes in the left waveguide. And this is a trivial statement, but this reflection matrix is not a Hermitian matrix. This is the whole point. The main point of our work was to show that this reflection matrix, which is obviously not Hermitian, is also happens to be a matrix which is topological. So you can see that the reflection matrix is topological from older work, which shows that the reflection matrix can be used to determine the Chern number of this Chern insulator. So the reflection matrix is topological because it describes reflection from a topological insulator. So here's how this works. In order to determine the topological invariant of the system from the reflection matrix, you can go in an infinite geometry, or if you don't like an infinite geometry, you can also use a cylinder. But here I'm plotting an infinite geometry. So now the boundary between the waveguide and the Chern insulator is infinitely wide. It's translationally invariant, so I can describe the reflection matrix in terms of a momentum parallel to the boundary. And it turns out that the Chern number of the Chern insulator is given by this formula. It's the winding number of the determinant of the reflection matrix. This tells you the Chern number of this blue system. Now you have seen this formula before. Here there was a big H before, and now there's a little R. Here there was a big W before, and now there's a big C. But this is exactly the topological invariant of the Hatano-Nelson model. This means that, according to this formula, the reflection matrix from the boundary of a Chern insulator is topologically equivalent to the Hamiltonian of the Hatano-Nelson model. They have the same topological invariant. And therefore, they should show the same signatures of non-Hermitian topology. For instance, if I look at the spectrum of this matrix, non-zero Chern number, here Chern number equal 1, this means that the spectrum winds. And indeed, here, this is a calculation that shows numerically that the spectrum of this reflection matrix winds around the unit cell. This is a two-band system, so it has 2 orbitals per unit cell. Therefore, the reflection matrix is 2 by 2. The reflection matrix has 2 bands. So band number 1 starts over here at 0 momentum and goes through the top half of the unit circle in the complex plane, and band number 2 goes to the bottom half. And together they form one complete winding around the unit circle. Question? No question.
No question. No, keep going.
Okay. So this is the bulk spectrum of this reflection matrix, and just like the Hatano-Nelson model, it winds around in the complex plane. So there should be a non-Hermitian skin effect associated to it. There should be a boundary signature associated to this non-zero topological invariant, which happens to be the Chern number. And it turns out there is. If I go to a finite geometry, now this is something you would do in real life, because cylinders are hard and infinite systems are very hard in real life, but something finite can probably be done. So this is a waveguide which has a finite width. It's connected to a Chern insulator that has a finite width. And I see the eigenvalues and eigenvectors of the reflection matrix. Now, the reflection matrix is finite size, so you see there are some discrete eigenvalues which are positioned inside of the unit circle. And if I look at the eigenvectors associated to these eigenvalues, I see that all of them are exponentially localized on one boundary of the system. This means on one boundary of this waveguide over here in real space. Now, physically, this is different from a Hamiltonian. So the meaning of eigenvalue and eigenvector is not the same in a reflection matrix as in a Hamiltonian. The way to understand what these plots mean on a physical level, you can do by writing down the full equation. So these are the waveguide modes I showed you before. These are incoming. They have this sign and this transversal profile. And eigenvector means that the reflected wave, which is automatically has the opposite velocity, but this reflected wave has the same transversal component of the wave function. So on a physical level, saying that something is the eigenvector of this matrix means that if you were to have, by some kind of process, a incoming wave which has been selected to have this particular transversal wave function, then the reflected wave will also is guaranteed to have the same exact transversal wave function. So this means you've hit an eigenvector of the reflection matrix. The eigenvalue associated to this reflection matrix is complex. They are plotted here. They're definitely complex. And what they mean physically is they describe the process of reflection itself. So the amplitude, the modulus of this complex number tells you how much the wave is reflected. So over here, close to the unit circle, I have a modulus close to 1. This wave is almost fully reflected, whereas over here, I'm close to the origin of the complex plane. This wave is mostly transmitted. Very little of this wave is actually being reflected. The phase of this complex number, however, tells you what is the phase shift between the incoming and the outgoing wave. So this is a different physical meaning of a complex eigenvalue. Here, it's not clear what would be the physical meaning of splitting this into a real and imaginary part. Instead, here, the meaning of the complex eigenvalue is not given by the real and imaginary part, is given by the modulus and the phase, which describes how much is reflected, and when it's reflected, what's the phase difference compared to the incident wave. So this is a way of obtaining non-Hermitian physics from backscattered waves. And it produces the boundary signature of non-Hermitian topology, which is the non-Hermitian skin effect. So what about the bulk signature? Then in the bulk, there was this net current, which flew in the direction of the larger hopping. And I told you that if you time evolve or if you apply the Hamiltonian, you're going to get a wave packet which is slightly shifted. And if the reflection matrix, since the reflection matrix is topologically equivalent to the Hartano-Nelson model, then applying the reflection matrix should produce a lateral shift. So this is a cartoon of the behavior. It's you send in an incident wave. This wave gets reflected. This means the reflection matrix acts on this incoming state to produce an outgoing state. But the outgoing state is not at the same position. The outgoing state has been shifted. So this is a signature of the non-reciprocal, the non-zero net bulk current associated to non-Hermitian topology in the Hartano-Nelson. So here's a simulation showing this. This is an initial incoming state, and it has this profile along the transversal direction of the waveguide. And as you reflect multiple times, so we imagine that here there's a churn insulator, and far away on the backside, there's a perfect mirror. So this wave bounces back and forth many times. Every time it hits the boundary of the churn insulator, it gets shifted a little bit, which is a signature of this non-zero net current, until it reaches the boundary of the waveguide over here, and here eventually it will get transmitted to the other side through this chiral edge state. Now, okay, there is a very simple and down-to-earth explanation of this effect. You don't need non-Hermitian topology in order to explain this effect. There's a very simple understanding. The wave goes in, it populates this edge state for a bit, and then it goes out. But for the time that it stays inside this edge state, it moves together with the edge state. So the simple down-to-earth explanation is wave goes in, fills the edge state a bit, edge state moves, and when the wave goes out, it has been shifted. The abstract way of seeing the same simple thing would be to say this is a non-Hermitian signature of a non-zero topological invariant. And the advantage of seeing things in a more abstract way is that you can generalize. And this is what we have done. I'm not going to, I forgot to say this, yes. So this lateral shift is something that is known from optics. So this is called the Gauss-Henken effect. This was discovered by Gauss and Henken in this old paper. And in optics, Gauss-Henken effect means that the incident and reflected wave, they are shifted laterally. So you can see here in this cartoon, there's a lateral shift between the incoming beam and the reflected beam. So this is very similar to this lateral shift that we have here. But one important difference is that this shift happens even at normal incidence. So here in order for the Gauss-Henkin effect to work, the conventional one, you need to have this at an angle. If the wave comes in, if the beam comes in at an angle, then you can get a shift of the reflected wave. But if the beam comes in directly perpendicular to the sample, the outgoing wave, the reflected one, will be at the same position. Here, this is a kind of non-reciprocal Gauss-Henkin effect. So this is already a difference to the conventional one. Even if the wave hits the sample perpendicularly, you're still going to observe this shift. And by using, like I was saying before, in an I hope the good slide comes now. Just by using the non-Hermitian topology and thinking this in an abstract way, we've managed to generalize this to a wide range of topological insulators. So it turns out the reflection matrix of a topological insulator is topological. So what we can prove is that for any strong topological insulator in these Wigner-Dyson classes, so A, A1, or A2, in any dimension, you will have a reflection matrix which shows non-Hermitian topology. So what we can show is that in the infinite geometry of a d-dimensional TI in these symmetry classes, the spectrum of the reflection matrix must cover the full circle of the complex plane. And if you introduce one boundary in this d-dimensional setup in order to have a semi-infinite system, then the spectrum of the reflection matrix must cover the whole entirety of the disk inside. So this shows you on a spectrum level that that this reflection matrix has non-Hermitian topology in it in general, and this predicts the fact that you should be able to see this kind of lateral shift, this Gauss-Henkin effect, also in a general TI, as long as it's
question. So here you need a genuinely semi-infinite construction, right, to fill completely the circle. Because yes, earlier, in your example earlier, we just saw some eight like curve of eigenvalues, right? Yeah, on the left.
So this is a discrete set of points.
Discrete for finite size.
Yes, yes. And so if bigger system, more points.
Yeah, but here you don't have a zero eigenvalue, so nothing is completely transmitted.
That's this true. Yes.
Is this an accident or something that you could predict it?
So I would generally not expect there to be in this setup an eigenvalue exactly at zero. So if you compute the two-terminal conductance of the system, you will see that numerically this is very well quantized to 1. The two-terminal conductance of the Chern insulator is equal to the number of edge states. So if I did that, I would get 0.999999999, and the way you get that is you sum up all of the eigenvalues of all of the transmitted modes. So there's one mode which gets transmitted, 70% of it gets transmitted. There are other modes which only get transmitted like 2%, and the sum of all of them turns out to be exactly 1, which is why you expect to see E square over H conductance in a Chern number 1 insulator. Okay. So this is not related to the value of the conductance itself. So having or not having an eigenvalue at 0 here is not necessarily telling you anything about quantized conductance. However, the fact that this is Chern insulator tells you that these wave functions must be localized on the boundary because of the non-zero invariant, and it also predicts on a general level this kind of shift, lateral shift.
Okay, but in principle, you could repeat the same exercise for the transmission matrix, right?
In principle, yes, and I think some people have done this. Some people have looked at transfer matrices, for instance, and they have associated that to some kind of non-Hermitian topology, as far as I know. What we did is we looked at the reflection matrix because the transmission matrix is not necessarily guaranteed to be a square matrix. So working with a square matrix is something that I enjoy more than working with a rectangular matrix. And also, this is a formula that we had worked on some years ago. And when we saw the Hatano-Nelson topological invariant, we said to ourselves, wait, we remember this formula. We know this formula. So this is how we started the idea for this project. But in principle, I think yes, you could use also the transmission.
Okay. Thank you.
Okay, so this was in general in different dimensions and in these symmetry classes. And now, how do you measure this? Now I will make the claim. The claim is that these effects which I have shown you, they are realistically measurable in the lab with currently available technology. Now I'm a theorist, and usually you should be extremely suspicious when a theorist tells you that something is realistically possible in the lab. Usually you shouldn't ask theorists about that. But still, my claim is that these things can be measured in the lab. And the reason why I say that is these things have been measured in the lab. So this is an experiment from 2015, which measures the eigenvalues of the reflection matrix of a effective churn insulator. And you can see that these eigenvalues wind around the units, wind around the origin of the complex plane. This has already been measured, the winding of the eigenvalues of the reflection matrix, even though the connection to non-Hermitian topology and the connection to non-Hermitian skin effect has not been realized. Here's a more recent work, a second one, which actually measures the non-reciprocal Gauss-Henkin effect. Again, without realizing that this is actually a connection to non-Hermitian topology. This is an optical system, so they have here a barrier which behaves like the boundary of a churn insulator. So in their sim, they have this leg here which allows them to send in an incoming wave at this particular position. And in the simulation, they expect that the incoming wave, which is perpendicular to the sample, will get shifted up or down depending on the direction of this chiral edge state. And this is what they see in the experiment. You actually see it goes up and it goes down depending on effectively the churn number of this system. So non-reciprocal Gauss-Henkin effect has actually been measured. It would be nice to design an experiment which can also measure the eigenvectors of the reflection matrix. So then you would see that they are exponentially localized on the boundary of the system. Good. So in conclusion, I have shown you that you can get non-Hermitian physics without gain and loss. What this means is that there are many operators in life, and some of these operators, they are Hamiltonians, and some of these are not Hamiltonians. And for some of them, it turns out that they are non-Hermitian just by themselves, and you don't have to work very hard to get, for Hamiltonians, okay, you have to do some stuff to get it to be non-Hermitian. But for the reflection matrix, which maps incoming waves to outgoing waves, that's just non-Hermitian by itself. And it turns out if you backscatter from the boundary of a topological insulator, the reflection matrix is also topological. And therefore it has some properties associated with this topology, like the presence of a non-Hermitian skin effect. Further, this means that you can produce signatures of non-Hermitian topology without worrying about some of its practical drawbacks, such as the problem of dynamical instabilities. This is something that I didn't mention before, but if an eigenvalue of a Hamiltonian has a negative imaginary part, this means that it will decay in time. And this means you have to measure it fast because it's going to go away and it's going to disappear. If an eigenvalue of a Hamiltonian has a positive imaginary part, this means somehow this wave gets amplified. So you have to be careful when you do this experiment because you can't amplify waves forever. Eventually your experiment is going to burn if you pump more and more and more energy into the system. So regime of dynamical instability is when a physical system has overall more gain than it has loss. This is an unstable regime. With reflection matrices, you don't have a physical meaning to the real and imaginary parts. Instead, the above and below the real axis eigenvalues just means that the phase difference between the incoming and the reflected wave is positive or negative. So therefore, you can have non-Hermitian systems which don't have problems in terms of decay and amplification in the sense of having unstable regimes. Yeah, this works for any strong TI in these three symmetry classes. The reason why we restricted ourselves to these symmetry classes is that they're the only ones where we actually managed to show this in a model independent way. We have checked for other symmetry classes and other specific systems that it still works, but I don't know how to show that in general, except in the Wigner-Dyson classes. That's where it works so far. Yeah. This means that you should expect to see a non-reciprocal Gauss-Hankin effect in all of these different types of topological insulators. So if you send in an electron at the boundary of a 3D TI, the outgoing state should be shifted in a particular direction that depends on its spin. And in general, this should happen for all of these strong TIs. And this can be and has been measured. And in the future, you might think of extending this to other kinds of systems, such as topological semi-metals or higher order topological systems. So that's it. Thank you.
Thank you very much.
Thank you very much.
Any questions, comments to Cosma?
Yeah, I have a short question, if I may.
Go.
Thank you. So yeah, thanks for the nice talk. You mentioned those Wigner-Dyson classes A, A1, and A2, but in your example that you showed, everything looked completely clean. The system is clean, not disordered. So in what sense are you talking about Dyson-Wigner? Is it just the symmetries? You don't refer to any disorder. Just the symmetry, not disorder.
Just the symmetries, yes. So class A means you don't have time reversal, particle hole, or chiral symmetry. A2 is you have a spinful time reversal, like in a time reversal system with spin-orbit coupling. And A1 is spinless time reversal.
Mm-hmm. Okay. Thank you.
More questions, comments? No more comments and questions. That means it was all very, very clear.
It was clear.
Good.
Let's thank Cosma again. Thank you very much for the nice talk. Thank you.
Thanks.
Okay. Thank you for coming.
Thank you again for having me. It was good.
Thank you.
Bye.
Okay. See you. Bye.
Bye-bye, everybody.
Bye.
In 2 weeks.
In 2 weeks.
Bye, everyone.
Hello.
Bye, Zana.